You may have heard at some point that the brain has 100 billion neurons. You may have also heard that each one of those neurons has about 10,000 connections. So if we think about each connection as some kind of an information processing unit, then we've got about a quadrillion information processing units, which is just a staggering number. It's 15 times as big as the global GDP. It would take only about 100,000 people, so like the population of Boulder, Colorado, to equal all the computing power of every single computer, cell phone, what have you, on the entire planet. The question arises then, how exactly does the brain coordinate all of this massive computing resource? And it's a tricky issue. You know, imagine if every time you sent a message on your cell phone, it went to every single one of your contacts. Not ideal. But yet each neuron has 10,000 connections. And every time it sends out an electrical pulse, that electrical pulse is going to travel out to all 10,000 of those connections. So how do you make sure that only the right connections listen to and process that signal? Well, back in 2005, Pascal Fries published a paper where he put forward this idea of communication through coherence. And this figure here shows you the basic idea. So the orange, aqua, and black dots are representing kind of areas of the brain. And then over to the side, you see those oscillations, those waves. And those waves are representing ongoing electrical activity in the different regions. What you can see is that the aqua and the orange regions are oscillating in sync with each other. When one of them's up, the other one's up. When one of them's down, the other one's down. But the black area is oscillating out of sync. So then what ends up happening because of this is the spiking activity, which is those vertical hash marks in the figure. The spiking activity of the aqua and the orange areas, it arrives at the other area during a period of excitation when the voltage is high. And this puts it at a higher probability that those signals will actually be listened to and processed. Whereas the signals coming out of the black area end up arriving at a time of low excitation or low voltage. And this ends up meaning that they're not going to get listened to. So we can see that by having different areas of the brain tuning in at different frequencies to each other, you can create privileged communication between them on a millisecond timescale even, without actually having to alter the anatomical wiring in the brain. And this has been a really influential idea. Thousands of papers have been published citing this idea and using it as a way to make inferences about what areas of the brain are communicating with each other and when. There might be a problem though. So in the paper I'm going to tell you about today, Marius Schneider and Martin Vink and their colleagues, they took a look at a bunch of different data sets and did a huge computational modeling effort to try and figure out what exactly is it in neural activity that leads to these measures of coherence. And is it truly communication? So what they found was that no, it doesn't seem to be. It seems like actually coherence ends up being a measure that's more sensitive to the power of an oscillation or the amplitude or volume of an oscillation in one particular area, not two, and the connection strength or anatomical connection strength between areas. It's not really a measure of communication so much as it is a measure of signal in one area and the anatomical connections of that one area. Well, that's a little bit unfortunate, but there is a silver lining in that it gives us more insight into the way that neural communication really takes place. Hi there, I'm Adam Dede, and this is a Neuroscience Journal Club, where I try and bring you a weekly discussion about a recently published peer-reviewed article from the world of neuroscience. So why is this important anyway, this idea of coherence and neural communication and all that? Well, it is kind of a core issue in all of neuroscience. You know, if we want to understand the way the brain works, we obviously need to understand what's the language of communication that the brain actually uses. How does it send signals between different processing elements in the network? And let's just jump right in then and think about what is it that Schneider and colleagues actually showed us. I think it gets more concrete as we look at the data. So they first took a look at some data that had been collected in monkeys. And what they were looking at specifically was signals that had been collected from the parietal cortex, an area called 7B, and the prefrontal cortex, an area called 5F, or F5, sorry. And what they found was that there was strong coherence between these two areas at about 20 cycles per second, or 20 hertz. So according to the coherence, or the communication through coherence theory, this would tell us then that there's communication going on between these two areas, and it's happening at about 20 cycles per second. That's the frequency that both of these areas are tuned into and using to communicate with each other. But the story got a little bit more messy when Schneider and colleagues looked then at what was the power in the 20 hertz signal in both of these areas. And what they found was that although 7B had really strong power, the volume was really high in area 7B at 20 hertz, that just wasn't true for area F5. So that's a little weird. Like, how can it be that these areas are communicating at this particular frequency, but yet only one of them actually has a signal at that frequency? Well, you could imagine that could still work, where if it's just a situation that the volume has been turned down on the 20 hertz signal in area F5, but maybe we have a situation where the spikes are still well aligned to that oscillation, so there's still good communication going on. Well, they looked then at how well the spikes locked on to particular phases, so either maybe the top or the bottom of those waves, how well did the spikes lock on to particular phases of the 20 hertz oscillation? And what they found was that that parietal area, area 7B, had really good phase locking at 20 hertz, just like you would expect if 20 hertz is really this important signal for this area. But the same thing was not true for area F5. So we've got this really weird set of findings then. We've got strong coherence at 20 hertz between these two areas, but the prefrontal area F5 does not have any power at the coherent frequency, and it does not have any spike phase locking at the coherent frequency. So what's happening? So next, Schneider and colleagues wanted to take a look and see if the same thing could be found in other areas of the brain, other model systems even. So they took a look at some data that had been collected in mice. And this time they were looking at data from the lateral geniculate nucleus, or LGN, and the primary visual cortex, or V1. Now, it's important to know that LGN projects axons anatomically directly to V1. So we know that there's good anatomical connection between these areas. And when they looked at the electrical signals that had been recorded in these areas, they found that there was strong coherence. And that coherence happened specifically at 55 hertz. And you can see here it was actually even anatomically specific. So what we're looking at on this graph, on the x-axis you're looking at frequency, and on the y-axis you're looking at depth in micrometers in the primary visual cortex area V1. And what you can see is that the coherence was primarily limited to layer 4. So we've got this very specific signal that's coherent between LGN and V1 at 55 hertz in layer V1 in layer 4 of area V1. So they wanted to take a look at some of the same things they'd looked at in the monkey data, and so they went to the spike phase locking values. And what they found was that while the LGN, just like the parietal cortex in the monkeys, while the LGN in the mice had strong phase locking to the coherent frequency at 55 hertz, there wasn't any phase locking going on in area V1. So it's, again, just like with the monkeys. So they wanted to know now, okay, what's really going on? What's causally happening here? Is there something that we're missing that could actually be some real communication? So if you think about communication for a second, it's not just yelling into the wind, right? Communication involves some kind of a back and forth. You need to have the receiving person or the receiving brain area has to take in the information that's being communicated, has to process it, and has to respond in some kind of a way. And if you don't have that, if you don't have that taking in, that processing, and that responding, then you don't really have communication. You know, like I said, you just have yelling into the wind. So in order to try and get a handle on this, they went to an optogenetic manipulation. So in optogenetics, it's possible to use the shining of a laser inside the brain in order to turn on and off certain neural responses. And in this case, what they're going to do is every time they shine the laser, the cells in area V1 are going to essentially stop firing. And you can see that on this graph here. In blue, we see times when the laser is being turned on, and in black, we see a situation with no laser being turned on. And on the y-axis, you're looking at the firing rate of neurons in area V1. So what you see is when the laser gets turned on, the firing rate essentially drops to 0. So if you think about two people talking to each other, what this would essentially look like is two people are talking to each other and then all of a sudden one of them just stops talking. And you can imagine that should dramatically change the nature of communication between those two people if one of them just goes silent. So they took a look then at what happened to coherence. And what you can see here is that even though area V1 is essentially going silent with this optogenetic manipulation, nothing's really happening to coherence. Okay, so coherence really is not looking like it's part of communication, at least not in these situations, not in the monkeys, not in the mice, not with this optogenetic manipulation, just data set after data set, we're seeing that it's just yelling into the wind. So what's actually going on though? So the next thing that Schneider and colleagues did was they developed a computational model. And in their computational model, they were able to actually put mathematical values onto the contribution to coherence of different aspects of neural activity, and specifically the power of the neural oscillation, the spike phase locking, the strength of anatomical connection between areas. All these things could be taken in their model. And what they found was that the things that really determined coherence were the power of the oscillation in the sending area, the spike phase locking in the sending area, and the strength of anatomical connection between the two areas. Whatever happened in the receiving area really didn't matter. And that tells us then that coherence is not really telling us too much about communication. It's just telling us about what's happening in the sending area, not the receiver. Now, one exception to this was if both areas happen to have strong power in the same frequency, then the only way that you get coherence in that frequency would be if those areas were actually showing some real evidence of communication and some resonant properties between the two of them. And you can think about this again, thinking about two people talking to each other. If two people just happen to be talking continuously, they have a high volume, a high amplitude, high power, we could say, they're not really communicating unless they're taking turns, responding, listening, all of the things that happen in a normal conversation. So when both people are talking, it requires resonance, coherence between the communication before they actually can be said to be communicating. By contrast, you could have a situation where just one person is talking on their own, and maybe that conversation that they're having with themselves is very coherent, but there's no actual communication going on unless there's a receiving partner that is responding, listening, processing the information. So at the end of the day then, all of this can feel a little bittersweet. Essentially, the results of Schneider et al. Are kind of calling into question thousands of results that have been based on the idea that coherence can be taken as evidence for communication. So that's a little frustrating that we see, thousands of papers that kind of get called into question. But I think what's cool, though, is that this is a real step forward in our understanding of what aspects of neural activity go into coherence and what aspects of neural activity we can think of as being markers of true communication. So it's not any one thing. The brain is multifaceted. There's many ways to look at neural signals. And I think what we're seeing here, then, is that the power of the neural oscillation, the spike phase locking to that neural oscillation, the strength of anatomical connection, and the resonance between areas, all of these things are contributing to neural communication, and it's really important to think about all of them when you're trying to make inferences about whether or not two areas of the brain are actually communicating. So that's it for this week. If you've got any interesting insights or inferences or questions that pop up for you as a result of thinking about this information, please jump down into the comments section below and leave a comment. If you really like the content, I would really appreciate it if you supported me on Patreon, and the link is down below. And feel free to subscribe and like, and I'll catch you next time. Thanks.